A team of astronomers pointed to the most powerful telescope humanity has ever built at a planet 124 light-years away. And what came back in the data sparked one of the most intense scientific debates in recent memory: a possible chemical signature of life, the kind of gas that on Earth only comes from living organisms. But before you get too excited, here is the honest truth. Not every scientist studying this data agrees on what it actually shows, and that disagreement is exactly why this story is still unfolding right now. We are talking about K2-18b, a distant exoplanet that has become the single most argued over world in modern astronomy, and the James Webb Space Telescope's ongoing search for signs of life hidden in its atmosphere. If you have seen headlines claiming Webb found a fully habitable planet, or even signs of alien life, stick around, because the real story is far more careful, far more scientific, and honestly, far more interesting than any single dramatic headline could ever capture. Let's start with the basics, because understanding this planet properly changes everything about how you should interpret the excitement surrounding it. K2-18b orbits a small, cool, red dwarf star located somewhere between 111 and 124 light-years from Earth, depending on which research team's measurements you look at, sitting comfortably within what astronomers call the habitable zone, the region around a star where temperatures could theoretically allow liquid water to exist on a planet's surface. First discovered back in 2015, K2-18b is significantly larger than Earth, with a radius roughly 2.5 times greater and a mass around 8.5 times heavier, placing it in a category of planets scientists call subneptunes, worlds that do not have a direct equivalent anywhere in our own solar system. Researchers, led primarily by astronomer Niku Madhusudan at the University of Cambridge, have proposed that K2-18b might belong to a theoretical class of planets known as Hycean worlds, a term combining the words hydrogen and ocean. The idea is that a Hycean planet would have a deep, possibly global ocean of liquid water, sitting beneath a thick, hydrogen-rich atmosphere, creating exactly the kind of environment some scientists believe could potentially support microbial life, even though the surface conditions would look nothing like anything found on Earth. It is important to understand that this Hycean classification remains a hypothesis, not a confirmed fact. Nobody has directly observed an ocean on K2-18b. Its interior structure remains fundamentally unknown, pieced together from indirect atmospheric measurements rather than any kind of direct observation. That brings us to the actual discovery that sparked this entire debate. In 2023, using Webb's near-infrared instruments, Madhusudan's team detected methane and carbon dioxide in K2-18b's atmosphere with strong statistical confidence, an important finding on its own, since it supported the idea of a hydrogen-rich atmosphere consistent with the Hycean theory. But buried within that same 2023 data was something else, a faint, low-confidence hint of a molecule called dimethyl sulfide, often shortened to DMS. On Earth, DMS is produced almost exclusively by marine life, primarily by tiny ocean organisms called phytoplankton. Finding even a weak signal of this molecule was enough to generate genuine excitement, though the team was careful to note the detection was far too uncertain to draw any real conclusions from at that point. Before we go further, if you appreciate content that actually respects the science instead of exaggerating it for clicks, go ahead and tap that like button right now. It genuinely helps this channel keep making videos exactly like this one. Then, in April of 2025, the same research team returned with new data, this time using Webb's mid-infrared instrument, a completely different tool operating in a different range of light entirely, observing the planet using wavelengths that had never overlapped with the earlier near-infrared study. This time, the signal strengthened. The team reported evidence for dimethyl sulfide and its close chemical cousin, dimethyl disulfide, known as DMDS, at a confidence level of roughly 3 sigma, meaning there was only about a 1 in a few hundred chance the pattern showed up, randomly by pure statistical accident. Even more striking, the team estimated that if these molecules really were present, their concentration in K2-18b's atmosphere could be thousands of times higher than the levels typically found in Earth's own atmosphere. Co-author Mons Holmberg, a researcher at the Space Telescope Science Institute, described watching the results hold up consistently across extensive independent analyses and robustness testing as a genuinely striking moment for the research team. That consistency across two completely different instruments, observing 2 different wavelength ranges, is part of why this particular result generated so much attention across the scientific community, far more than most exoplanet atmospheric studies typically receive. However, and this is genuinely important, 3 sigma confidence, while promising, is nowhere near strong enough to count as a confirmed scientific discovery. The gold standard in physics and astronomy for declaring something a true discovery is 5. Sigma confidence, representing odds of roughly 1 in a few million that a result occurred purely by chance. 3 sigma results, while statistically interesting and worth pursuing further, have historically turned out to be false alarms, often enough that serious scientists are trained to treat them with real caution rather than immediate excitement. If you are new here and enjoy watching science actually explained honestly, without the exaggeration, now would be a great time to hit that subscribe button, because there is a lot more of this waiting for you. That caution turned out to be well justified. Multiple independent research teams began reanalyzing the same publicly available Webb data almost immediately after the April 2025 announcement, and the picture that emerged was far less clean than the initial headlines suggested. Researcher Jay Taylor published a follow-up study specifically challenging the original team's data analysis methods, arguing that the statistical framework used to identify DMS and DMDS in the spectrum was too narrowly constrained, potentially skewing the results toward finding exactly the molecules the team was already looking for. A separate reanalysis by researcher L. Wellbanks and colleagues raised similar concerns, pointing out that the specific set of candidate molecules chosen for the original analysis significantly influenced which compounds the model concluded were present, a subtle but scientifically important criticism that cuts to the heart of how these kinds of atmospheric studies actually work. Then, in July of 2025, a NASA-led team uploaded their own independent analysis using a broader, more comprehensive set of possible atmospheric molecules than the original study had considered. Their conclusion was considerably more cautious. While their analysis did confirm that K2-18b's atmosphere is genuinely water-rich and chemically complex, they found no conclusive evidence supporting the presence of DMS specifically. And their study emphasized just how genuinely difficult it is to confidently interpret faint spectral signals like this one, given the current limits of the technology and the sheer complexity of exoplanet atmospheric chemistry. By 2026, the overall scientific consensus on K2-18b had settled into something considerably more measured than the initial 2025 headlines implied. A survey published in the journal Nature Astronomy found that only a small fraction of participating astrobiologists, roughly 6.5%, actually agreed with the original claim that Webb had found strong evidence of DMS or DMDS in the planet's atmosphere. That is a genuinely important data point, not because it proves the original team was wrong, but because it shows just how far from settled this question actually remains among the scientists most qualified to evaluate it. There's also a deeper scientific question tangled up in all of this that goes beyond simply whether DMS is present or not. Even scientists who accept that these molecules might genuinely be in K2-18b's atmosphere disagree about what that would actually mean. Sun Kwok, a former president of the International Astronomical Union's Commission on Astrobiology, has pointed out that dimethyl sulfide has actually been detected before in interstellar clouds and even on a comet, environments with absolutely no life involved whatsoever. That means even a confirmed detection of DMS would not automatically prove biological activity. It would simply mean the molecule is present, leaving scientists with the much harder task of figuring out whether some unknown non-biological chemical process might be capable of producing it under the specific alien conditions found on a distant Hycean world. Conditions completely unlike anything found naturally on Earth. This is really the heart of why serious scientists keep pushing back against Dromet-Ike headlines calling K2-18b a confirmed sign of life, or worse, a fully habitable planet. Even in the most optimistic, best-case interpretation of the current data, all researchers have found is a statistically uncertain hint of a molecule that itself would not prove biological activity even if its presence were fully confirmed. That is a genuinely fascinating scientific lead worth continuing to investigate. It is not, by any reasonable scientific standard, evidence of a confirmed habitable world, let alone confirmed life. So where does this leave things heading forward? Madhusudan and his team have continued to defend their original analysis, arguing that the consistency of their signal across two independent instruments and wavelength ranges remains a genuinely compelling reason to keep investigating K2-18b closely. Meanwhile, critics continue pushing for additional, higher resolution observations, arguing that only significantly more data, ideally reaching that elusive 5 sigma threshold, could actually settle the debate one way or the other. Both sides agree on one thing at least. More observation time on K2-18b is needed before anyone can draw a truly confident conclusion, and additional Webb observing time has already been proposed to gather exactly that kind of higher quality follow-up data. What makes this story worth following closely, despite all the uncertainty, is exactly what it reveals about how real scientific discovery actually works. This is not a story about NASA hiding an obvious discovery of alien life from the public. It is the opposite. Every step of this debate has played out completely in the open. published in peer-reviewed journals, argued about publicly by researchers with access to the exact same raw data, each one testing, challenging, and refining the same set of observations using different statistical approaches. That messy, public, ongoing disagreement is not a sign that something has gone wrong with the science. It is a sign that the scientific process is functioning exactly the way it is supposed to, refusing to accept an exciting claim simply because it would be a wonderful thing to be true. It also helps to understand exactly why exoplanets like K2-18b are so difficult to study in the first place, because the challenge E is not simply a matter of pointing a telescope and taking a clear photograph. K2-18b is far too small, far too dim, and far too close to its own star to ever be directly photographed with current technology. Instead, scientists rely on a technique called transmission spectroscopy, waiting for the exact moment the planet passes directly in front of its host star from our point of view, then carefully measuring how starlight filters through the thin sliver of atmosphere surrounding the planet's edge during that brief transit. Different molecules absorb light at very specific wavelengths, leaving faint, characteristic fingerprints in that filtered starlight. Detecting those fingerprints from 124 light years away, buried within an incredibly faint signal, is an extraordinarily delicate task, one where tiny differences in analysis method can genuinely change what conclusions researchers walk away with. That difficulty helps explain why reputable scientists on both sides of this debate are being so careful with their language. Nikumadhusudan himself has consistently described the findings as requiring caution, explicitly stating in earlier announcements that this does not represent a confirmed detection, even while defending the overall strength of the evidence his team has gathered. That kind of measured language stands in sharp contrast to some of the more sensational headlines that circulated after the April 2025 announcement, headlines that stripped away nearly all of that careful nuance in favor of dramatic claims about alien life being found. It is also worth remembering just how young this entire field of research actually is. Before the James Webb Space Telescope launched, scientists had almost no realistic way of studying the detailed atmospheric chemistry of small, potentially habitable exoplanets orbiting distant stars. Webb changed that almost overnight, opening up an entirely new frontier of research that simply did not exist in any meaningful practical sense just a few years ago. That means researchers are still developing and refining the statistical tools and analysis methods needed to properly interpret this kind of data, which helps explain why disagreements like the one surrounding K2-18b are happening now, in these early years of Webb's mission, rather than representing some kind of unusual or alarming scientific failure. If anything, it is a sign of a young field working exactly as it should, testing bold claims rigorously before accepting them as settled fact. For now, the honest, accurate summary is this. K2-18b remains one of the most intriguing exoplanets ever studied, orbiting in chemically complex atmosphere that continues to genuinely puzzle researchers. Whether it hosts a global ocean, whether the AT ocean could support any form of life, and whether the faint chemical signals detected so far represent biology or simply unfamiliar chemistry happening on a genuinely alien world remain open questions that will likely take years of additional observation to properly resolve. If this kind of honest, carefully reported deep dive into real, ongoing scientific debate is what you come here for, make sure you are subscribed with notifications turned on, because K2-18b is not going away as a topic anytime soon. And there's a very good chance the next round of Webb observations brings us one step closer to finally knowing what is really happening in that distant, water-rich atmosphere. Whatever the eventual answer turns out to be, this is exactly the kind of careful, methodical, occasionally frustrating process that real scientific breakthroughs actually come from. One reanalysis, one challenge, and one round of additional data at a time. Every telescope pointed at K2-18b from now on adds one more small piece to a puzzle that may take years, possibly a full decade, before scientists can finally say with real confidence whether this distant, water-rich world is simply strange chemistry or something genuinely alive.